So, so yesterday we hinted at this, and we just kind of touched on it right here. Anytime the solid that you make, whether it be with Play-Doh in your mind or on the computer or whatever, anytime the solid that you make is going to have either a hole in it or it's going to be concave. Like what I said yesterday is, if it would hold water potentially, or if you could see through it, then you're going to need to use what's called the washer method. Okay, and that's not even up there. So let me put it up. Don't we kind of have to picture this? So if you want, use your calculator. If you can just picture this on your own, that's fine. But let's get a graph of this in mind, and I'll get one up here too. Whoops. So let's see here. Okay, you guys okay with that? I guess I can live with that. Okay, so from a graphical standpoint, you guys okay with the purple region? Okay, so then we're going to revolve this around the x-axis, and I want to kind of take you through maybe a thought process that you would experience if you were doing this problem totally by yourself. So step one, you get the graph up there. I want you guys to try to visualize this in your brain. What kind of a shape is this going to create? And it doesn't have to be a perfect picture. You don't have to be like this mental Picasso, making this thing work. Here's basically what you got to answer. Here's the question. If I did this rotation, I created this solid, would the resulting solid have any kind of a hole in it or any kind of a concavity in it? Yes or no? It would, wouldn't it? Can you see how this space, right in here, when rotated, that would create kind of that gap or that concavity in the middle of this? And so if you can visualize this, great. If you need Play-Doh later on, that's great. You can't use Play-Doh on the test. You can't use Play-Doh on the AP test. But we'll continue to kind of mess around with that over the next week or so. But if you notice this, if you see that there's going to be a concavity to this solid or perhaps a hole, then what you need to use is the washer method. Okay? So if you notice a concavity or hole, you need to use washers, not discs. Okay, so from a strategical standpoint, does that make sense? You visualize it, you see the gap, you think, okay, I've got to use washers. Can I help you guys with something on framework here? Because there's all kinds of little things that could get messed up. Here's my system. I honest to God do this because I don't want to mess stuff up. I don't want to mess up your quiz key and then have to go back and fix a bunch of stuff. So here's what I do. Once I recognize I'm going to use washers, I'm going to write out pi integral, and then I write big parentheses squared minus little parentheses squared. And then I need to write a dy or a dx here in a second. But for the moment, I've got it set up to where my pi's in there. And the big parentheses, that stands for the big R, right? The little parentheses stand for the little r. That's kind of my visual cue on that. Let's decide about the dy or dx now. Any thoughts on that? What do you think it's going to be? It's got to be dx. Why, Johnny? Yeah. So if I were to draw in a representative element, it would look something like that, and it's perpendicular to the x-axis, which is our axis of rotation. So it's got to be a dx rectangle. So all that stuff we did with the disk method, all those concepts still apply. Okay, so as you can see, if you fill this out the right way, if you go pi integral big R squared minus little r squared, we only have to fill in the radii and the limits. So let's get busy doing that. Limits of integration. If I've got a vertical representative rectangle, what's the pattern of accumulation? Is it left to right or is it up and down? This rectangle, left and right. Yeah, so we're going to go from the left edge to the right edge. So where would I start accumulating? At x equals 0. And wouldn't I stop accumulating at the intersection point, which is x equals 1? That's right. So it's going to be pi integral from 0 to 1. Now we got to figure out the radii. So the radius, the big radius, I think, I'll just do this in a different color. The big radius, wouldn't that be the distance from here to there in yellow? So if you think back to what we mentioned in the class, I guess it would have been yesterday, literally if you start on the x-axis and you move up, what do you call that? It's literally a y. So if you wanted to, you could, again, knowing that you're going to change this later, you could put a big y right there. And then wouldn't the little radius be what I am doing in green? It would maybe go from here to there. Isn't that the little radius? So then, that's just like a little y. But we know that both of those y's don't really belong in the end. We need to write something equivalent to those y's, but it's got to be in terms of x. So what could I replace the big Y with? Root x. Can I ask you why you chose root x?
Because it's the top function.
Let's be really careful. Let's use some better language. Top function, yes.
Because it's the function that determines the top of the area being calculated.
It's the bigger Y.
I'm going to say it this way. It's the function that's further away from the axis of rotation. Can I give you a little bit of foreshadowing on something? What if our axis of rotation wasn't the x-axis? What if it was some line up here? Now all of a sudden the further away function is not the top function anymore, is it? Now it would actually be the lower one would be the further away function. So that the language I'd want you to use would just be it's further away from the axis of rotation. So root x would go there. And what do I put in place of the little y? X squared. Yep, agreed. Okay, so I'm going to give you guys a choice here. If you just want to use Math 9 to evaluate this, that's fine. If you want to do it on a paper, that's fine. If you look at that and you think, oh my gosh, I hope you would never ask me to do this on paper, I would. So if you do feel like you're not confident, maybe you should practice that. Either way, let's figure it out. Ready, go? Could be. I just did the first two.
That would be 0.943 then.
I think it's 0.94249.
Oh.
So you can't double round.
248.
248.
Or like it
94248. Yeah, so you can't double round.
Right.
247.
How you guys doing? That number makes sense to you all?
Yeah.
Okay.
Johnny, you have
Yeah, he said that was 3, 5, or 10. Yeah, that makes sense. All right. So, your chance to ask questions right now. Don't be shy. Okay, fair enough. Let's then take a look at number 4. And we may or may not finish number 4. We'll see. Number 4's got 4 parts to it. So let's start. Let's start here with A. This would be a good contrast with what we just did. So I kind of feel like if you can understand the one we just did and have a decent handle on that one, I think you got a fair chance to do 4A. You got a nice graph there. You got everything you need. See if you can. Oh, and please notice the language says write but do not evaluate. So sometimes that will be the language that you'd see on a quiz or a test. And if that's the case, please don't waste the time going through even with Math 9. Just set it up and move on. So that's basically what this is. So I'll give you guys a moment to try that. Solve for x. Yeah, we're going to have to solve for x on both of these. So this one right here would be y squared is equal to x. This one over here would be 2y equals x. We just got to figure out which one goes where. Which one is the bigger radius, the curve or the line? The line's the bigger radius, yeah. So I would put, in that place, I would put 2y. And then in place of the little green x, that's where the parabola, the part of the parabola goes. So it'd be y squared. What do you guys think? Any questions? So this one just said set it up, and so that's all you really had to do. So for our final segment here, unless there's a question, anybody? Final segment here for today is going to be B, and this is where things are going to be different. So if you've been, can I finish my sentence? I want to finish this real quick. If you have been super confident with A, and maybe you were really confident with number 3, that's awesome. I think you'll find this is going to maybe shift your thinking just a little bit, or maybe you're nailing it just perfectly. I have no idea. But let's be open-minded about how this could go. Colin, your question?
Would you lose points on A if you did evaluate?
As long as you evaluated it correctly, no. You'd be fine. But if you went on and you did a bunch of steps and like one of them was wrong and it gave you the wrong answer, I'm going to go through, I'm going to trace through and be like, all right, did he actually do it right? Did he say anything wrong? And if you said something wrong, you probably just lose a point.
Really? Like
Yeah.
the wrong answer?
Absolutely. Especially if you're telling me that that equals whatever it is you got and that's not true. Yeah, I don't know.
You're under arrest.
Did you circle your answer?
No, if I just like left it like.
I don't know. I'd have to do some thinking about that one. Yeah. That feels like the moral of the story, doesn't it?
It does.
Okay, ladies and gentlemen. Hey guys, hey. We are going to finish B, and we have time. Let's make sure that we finish it before 3 o'clock. So here is that region again, like so. And here's the line, like so. But then when you read B, B reads differently, significantly from A. It says, take that exact same region, but now we're going to rotate that around the line y equals 5. So no longer are we going to rotate around the y or the x-axis. It's going to be some other line. So this is what we call, whenever we move that axis of rotation around a little bit, we call this a displaced axis of rotation. So it's not the x-axis, it's not the y-axis, it's some other line. And so what I'm going to do is sketch that in, and this is where that thing that I was hinting about earlier is going to change stuff. So y equals 5 would be up there somewhere, and I'm going to attempt to rotate around that. Okay, so I want to do this one with you, and you can see that we'll do some other ones like this in the coming days. So here we go. Step 1, the guys, and this first step is not silly, especially when you think about it in the context of a test. You know, this could be number 21, and the previous one was about related rates. The next one is about L'Hopital's rule, right? So being able to stop and visualize is good. When you visualize this solid, kind of like you think about the Play-Doh or the computer thing I showed you, do you guys picture something with a hole in it? You see it? And you don't have to picture it perfectly. You just got to realize, oh, there's going to be a hole in this. There's going to be a gap here. And so if that's the case, we've got to use washers. So I am immediately going to write volume equals pi integral big parentheses squared minus little parentheses squared. And then let's do the dx dy thing. What do you guys think? Is it going to be a dx integral or a dy?
Yeah.
It is going to be dx. Reasoning on that?
Because it's horizontal axis.
Yeah, it's horizontal and we need to be perpendicular to it. So it's going to be a dx representative rectangle. So, dx. So what I'm going to attempt to do here is I'm going to attempt to explain why we do what we do here in a second, but then I'm also going to give you kind of a way to formalize it too. So check this out. Big radius, I'm going to try to illustrate this in blue. Wouldn't the big radius go from there, let's try that again, to there? And so this is where if you think, hey, yeah, the higher function is always the bigger radius, isn't this where you're wrong? Because it's actually like the physically lower one is the one that's further from the axis of rotation. So how do I express this, right? Because if you think about it, if I drew in some other ones, like there's another big radius, you can see that no matter where I draw this, it's going to be a different radius than somewhere else, right? It's not constant. So how could I do this? Here's how I think about this. This up here, this axis of rotation, is the line y equals 5. And I'm going to draw it in like this. Let me get rid of something. Get rid of that. There's y equals 5. So here's how you do this. This from here to here. How would you describe that light blue line that I just drew? That is a y. That is correct. Couldn't you say that the dark blue line is the actual radius? Actually, I'll use big R. Isn't that the radius that I want? Okay. So if the distance from the gray axis of rotation down to the x-axis, how far is that distance? I'm sorry, let me be a little more clear. I'm talking about this distance from here to here. How far is that? 5. And if the blue distance is y, what is my radius? 5 minus y. And so when it comes time to plug this in, I'm going to put 5 minus y. I know that in the end I'm going to get rid of the y and replace it with something, but it's going to be 5 minus y. And then, maybe I'll use a big y right there. And then the other one, my little radius, I will put in red. My little radius goes from here to there. And don't we have the same sort of concept? Like I would say from that point to here, that's another y. And so to get this little radius, wouldn't I have to go 5 minus the smaller y? So I'm going to put 5 minus little y. So now to finally finish this out, I guess I need to put my limits of integration. We'll get that in a second. I need to replace the big Y with something. Is it the curve or the line that determines the big Y?
Line.
It's the line. And the line was x over 2? X over 2, all right. So I can replace that Y with x over 2. And then the smaller y is the curve. And that was root x?
Yep.
Root x. So that goes here. So sometimes there's a question about, does the displaced axis mess with the limits of integration? Remember, the limits of integration are simply expressing where do I start accumulating these washers and where do I stop? So am I accumulating from left to right or am I accumulating from bottom to top? Thank you, Zach. Left to right. So where would I start accumulating? Where would I stop? 0 to 4. That would be the whole thing right there. This would be doable on paper. Math 9 was available. You obviously know what to do. Okay? Guys, thank you very much. We'll kind of conclude this part on Friday and move into something new, finish things up next week. Have a great day. See you guys.